Good morning, everyone. So as usual, we will start at 11:10, and we will start as all previous weeks, except for the first week, with the quiz. And after the quiz, that will start at 11:10. You should be done by 11:25 roughly, in 15 minutes. And after that, we will go over the material I covered in today's lecture, this week's lecture. And I'm going to give you a few example problems related to this content so you can practice a little bit about, how to use this content and what kind of questions you can get about it. Okay. Any questions? Okay, then see you in a few minutes. Okay, I think your test should be ready in 3 minutes. You should be able to start it in 3 minutes. Any questions before that? So the schedule of this tutorial is as usual. You start with the small quiz test at 11:10 for people who join us later. And you should be done in 15 minutes by 11:25, after which we will go over the week's material covered in the Wednesday lecture. I'll answer some of your questions, and then depending on how much time we have, I'll show you a few example problems and how you can solve them with the techniques we learned in this course so far. Any questions? Okay, you should be able to start now. Good luck with the test. Most people have finished. I'm just waiting for a few last people to finish, and then we'll go with the tutorial today. Okay, so let's start the tutorial. As usual, please, if you can turn on your camera at least for some time, that would be very helpful. Okay, so let's start. So as was announced, I'll start with briefly summarizing what we covered in today's week. So the brief summary for week 4 is that we learn about this really cool concept of sequential circuits that can have memory. We learn about latches, we learn about flip-flops. So just go over that one more time and just to refresh your memories. So essentially we build latches out of simple units such as NAND and NOR with feedback. So those are the units that, you know, as one of their inputs, they use the previous output of themselves, right? We found that those can be useful in building, and then we build latches out of them, where essentially the output of one copy is connected with the input of another copy. So we built several different types of latches, and one of those latches was not R latch, right? We studied carefully, we look at its truth table, and we found that that SR inputs here, they had a conceptual meaning. They serve as set, reset gates, right? And depending on the input, we essentially can have different outputs, either 1 or 0, and essentially when we get both S and R set to 1, 1, then essentially the value of the cell is locked, so it's locked for the previous state. So someone on Piazza asked the question saying, what we build these latches and flip-flops, but how do they really store the memory? So this is the way they store memory. They store the state that is permanent. So by manipulating the inputs of the cell, right? If I try to build a memory based on SR latches or more advanced cells, I can give it certain input. If I want to get a memory cell that has 1 in it, so I can enter certain inputs into SR, then lock it into this value, and then later on, I can read this value, but sensing the output, right? This is a very high-level description of how we can get memory out of it, right? This is not going to be very efficient memory, but it would work. So those are conceptually the building blocks for the memory. So there are some race conditions. There were questions about that. I tried to answer all those questions on Piazza myself. Essentially, the problem is, since you had, like, I'll just repeat for people who might still not get how you get race conditions. So the problem, if you go from 0, 0, right, there are dependency on what would generate the output first, and depending on what comes here, this output into this input, or the other way, you might either get an intermediate state 0, 1 or 1, 0. Because of that, it might differ on which value you're going to get. So this is very, undesirable situation, because you don't want to depend on the speed of a circuit or some randomness on which value you're going to get. So to avoid that, we have our forbidden state. So Yeah, the Qt axis in Qt and not Qt means that it's really undefined because it really depends on what was at the circuit before, right? Like we don't know what Qt at the beginning was, right? If we never use this circuit and there was no power there before, we don't, like the state there is undefined, right? We didn't set it to anything yet ourselves. So at the time t, when we start to use that, there's only input here, but this output is not defined yet. So x means undefined. We try to solve these problems by, and in general instability problems, by introducing a clock. So we build a server latch with a clock, where essentially the clock C allows you to manipulate the behavior of the latch. So this is the way we build. We build another connector here, right? And the clock is often connected to a pulse signal that alternates regularly between 0 and 1. We study that the latch carefully, and it has some desirable characteristic, but it has also some things we don't like, which is essentially it was still flipping multiple times through the pulse. So then we work on something called D-latch that fix this problem and can give us a flip only once. And at the end of the day, we were building a flip-flops, right, with all these different latches. So combining SR latch with D latch, we can get something that was going to flip properly, right? So it can flip on the positive edge or the negative edge. So what does it mean flipping on the positive or negative edge? So positive edge means when I go from signal timer 0 to high power, right? That counts, it means it's positive. We're going from 0 to like 5 volts. And if you go from high to low, that's negative, trigger flip-flops. So essentially, we build a circuit called flip-flop, and this is the symbol used to it. And this guy is going to be triggered on, when signal goes from low to high, and that thing would flip only once over the cycle of the timer. So essentially, if you look at the waveform that I show at the lecture, you're going to see that the flip-flop changes its value when the pulse starts going from low to high, and then it goes from high to low and from low to high again, and when it flips again, right? So it doesn't flip in between. So it only flips once, and that's what you really want, right? That's essentially a very stable memory, right? Something we can use moving forward. Okay, any questions you guys have about that? So the question is, if we can change SNR when we want to change Q, why we need a clock? So this is why I talk about instability of the results. Remember, so the problem is that we don't like the conditions, the inputs under which, whereas there's some non-determinism, like race condition. We can deprecate them, but essentially that's still a not desirable situation. So you want timer to be able to control while things change, right? So otherwise, when I draw all the circuits without timing, remember I was always saying time t plus 1, but how are you going to control it, right? So you want to have a memory cell that, you would know that it changes periodically based, like, when to check it when the value flip. Because otherwise, let's say it shows you output 1, it keeps showing 1, you check, 1 nanosecond later, it's still showing 1. So how long do you need to keep checking until it flips? You don't know without the timer. So the timer guarantees that if the value is supposed to change, then after, whatever frequency of the timer or the clock change, the bit is flipped and you will detect it. So you don't have that uncertainty on how frequently I need to change. 5 times, 10 times, it's not clear otherwise. So clock is really needed for this circuit. You can't really manipulate them efficiently. They would have memory even without the clock, but it's not very usable, right? Ziyu, does it answer your question? So why would we need a clock for sure? Okay. Any other questions? Okay, there are no more questions. Let's look at an example here. So I encourage you to try it out yourself first before I show the answers, right? So So essentially, that's the whole purpose of the tutorial, right? You try it out with me and I'll show you the answers. And if it mismatches and what you got, you can ask questions, right? So here's the circuit, right? You just need, using pen and paper, try to fill in the values for Q and not Q, right? Based on different inputs. So you see here we had us and our inputs, right? We had the clock, right? And that's what you need. And by now you should understand the gates used here and what happens. And I use very similar circuits in the lecture, so it should be familiar to you. So I'll give you a few minutes to try it out. And then I'm not going to ask for correct answers. I'm going to just show you them one by one. But I'll let you first try yourself. So then you can see whether you got it or not. Okay, let's start doing one by one. So we will start with the first pair of states here, right? So S is 0, R is 0, and clock is 1. So the clock is high. So what's going to happen? Well, let's look together. So 0 and 1 and what's going to give us 0? Negation of that is going to give us 1. So here we're going to get 1, right? This is absolutely symmetrical. So we're also going to get 1, right here. Okay, what happens afterwards? Well, the problem is I don't really know what's coming out of this at the time t. So this is undefined. So if it comes here, if it's 1, then the value of this thing would be 1 and not would be 0, so it would be coming 0. But since I don't know what's coming in here, because if it would be 0, that would be the opposite result. So I really don't know at the time t first, right? So this is undefined. Okay, so this is why we don't like this state, right? So how about now trying R0, but S being 1, right? So we are looking at the second row of this table. So here now there are a difference because now this is 0. Why the 0? Because this AND gives me 1, negation of 1 gives me 0, so it's definitely 0. Now the cool thing about this part is because the 0 comes here, it doesn't matter what's coming out of here, it's definitely going to give me 1. And this 1 definitely going to be propagated here. And because I get this propagated and this propagated, I'm definitely going to get 0 here. So after a certain time, after this propagates, I'm definitely going to settle to 1 and 0, right? So if you wait long enough for signal to propagate, I'm definitely going to get 1 and 0 state here. So essentially set, reset, set to 1, reset set to 0, going to generate, sorry, this is going to generate as 1, 0 when they're, this is high. Okay, what if I go down with my timing? So I go from a positive 5 volts or something to the 0. Well, let's see. So this 0, 1 is not going to affect this one. This is still 1, right? Sorry. So if I'm going to do this 0, 1, this is still 0, this is still 1, so I'm going to get 1 here, right? And you had, let's see, here I was still getting 0 and 1, so it's still going to get 0, and this is still getting 1. So I'm unlocked at the previous state, right? So this is what the timer does for that circuit, right? When I go from high to low, I'm just stuck with the previous values. I can't really move, okay? So the values are stuck at 1 zeros. And that's part of the memory theme, right? So it's stuck there. So what if I go to all zeros, right? So what if I do set resets all zeros? So let's see. So if it's all zeros, this is obviously 1, this is 1, right? So I'm gonna get, we already had it, it's 1, 0. So let's look at the next one, 0, 1, 0. So this is this row, 0, 1, and clock is 0. So this is very symmetrical. There is not much difference from 1, 0. It's just 0, 1 is going to lead to this state, to 1, 0. And obviously, if I'm going to set C to 1, right, I'm going to get this 1, 0 here, and this is going to flip to 0, 1, right? So essentially, the high pulse here with the input 0, 1, going to give us the output. So think about it. If I want to build a memory cell, if I set up the outputs the way I want, I just need to wait some time, right, when the C switches from 0 to 1, and then it would make sure that the output switches to 0 to 1. They're not immediately. So if I set 0 to 1, but C was still at 0, it's still stuck at the old value. You've seen it, right? 0, 1 with 0 doesn't really change. You're stuck with the old value, 1, 0. But then eventually when C is going up, and it periodically goes up and down, I'm going to start to this value. So essentially, the circuit has something we want, right? It can flip to there. It can store the values I want, right? So if I give it 0, 1, it gets me output 0, 1, right? And it happens when it goes to the high value of the timer, right? So periodically it goes to that. And then when I get the value I want there, I can just switch to 1, 1 input, and then it's locked. So it's exactly what I want to have in memory. I want to be able to set the value I want, like it's like set, store into memory cells. And then after I store it, I can lock it for as long as you want. And next time you want to read or change it, right, you can get access, read from the value or rewrite the value, right? So it's still, we didn't build the registers or anything yet, but you already see the primitive that can help us. Any questions, guys, about that? Is it clear what I just did? Is the truth tables always sequential? So what I was showing you, it can be done in any order. So it's like it's not dependent on the order of anything, right? So when C is positive triggers and then S equals to Q and R equals not Q, is this always true? No, this is just for this circuit. Remember, the circuit can be in the positive triggered, it is the way it's implemented, right? But you can have other, like, negatively triggered circuits, right? But yes, essentially in the positive triggered circuit, that's what we want to get. It's the most intuitive way if you think about it. When I set inputs to 0 and 1, I want the output to be 0 and 1, right? So, okay. Any other questions? So that's another little more tricky questions. So this questions is using some of the notations that we learned. So you see there is two things here, right? We have D-latch used in, at the top and at the bottom, and one of this has negation, right? So essentially, what we want to see is how essentially the output QL and QF behaves in this case. So look at it. So remember, those latches are built such that they are affected by their timing and the inputs into them, right? So input D is used both here and here, right? The difference is that this one uses the timer without negating it, right? And this one is use negation. So let's look how it's gonna, I'm just gonna help you. So essentially what's gonna help is at the beginning when C is low and D is low, then these guys are also low. There's nothing really changing them. There's like no signal going through them. Remember, when we build these latches, we really need the timer to go up for something to happen. So what happens next is when the timer goes up, right? When the timer goes up, if it happens that D at this moment was also high, then it's gonna go QL going up because it's positively triggered, right? And then if the signal D goes down, this thing will also goes down, right? And then if D goes up, this one also goes up, right? But later on, you see here, if we go into this state later on when the C is low, this one is just always high. And it's repeated again, right? So you see how it changes over time, what shape it has. Then if you look at QF in contrast is more stable, right? So the circuit for QF, due to this ability, to do negation, right? So it's positively charged, and by the ability for it to essentially use D-latch twice, right? It's able to only switch once. So remember, this is like a proper flip-flop. So this is like just a piece, and this is a proper flip-flop, right? That's what we're comparing. So essentially, if you look at this circuit, this is just one latch, and that's how it's going to behave. You can distinguish between the two states, but it's not looks perfect. Well, these guys look amazing, right? It's affected by the positive charge going through the C signal, right? And then it stays like that all the way. And then when it needs to go down, right, it goes down, right? So it's exactly the way it should be, and it's affected directly by the value of D. So you see here the D is high, so it goes up together with this. And then here D happened to be low, so it's going down. And it stays like that for the whole timing period. QF is positive edge triggered. You're correct, Ivan. Yeah. So you see it's triggered, right? And so here it's triggered with D being equals 1, right? Okay. So here there's another questions that similar in spirit. So you can essentially build a lot of units like D latches, SR latches, and now we can make a lot of different combinations with them, like including the flip-flop. So here the question is, assuming that the Q outputs of both flip-flops starts off low, what will the value of X and Y be over the next few clock cycles? You can assume that those latches are positive edge triggered. So again, you can experiment at home, but I'll just show you in the interest of time how it's going to work. So really, this is a properly built, D latches, and they're essentially like a flip-flops that are nicely connected with each other. So essentially what's going to happen, they actually behave the same way, as you can look on this figure. So both at the beginning, when you start with zeros, right, when the clock goes up, if you look here, right, what's the input here? So you start with the low, so your signal is low, right? This goes as an input here, and this goes as an input here. So they had the same input really, right, at the beginning, right? Because both starts with low. And then you use, time negation. So it's essentially, it's activated when times goes from low to high. And that's what happens here. It goes up. So essentially that triggers the output here to go up, right? And it's gonna stay like that because the second part here serves as a proper secondary flip-flop for it. So essentially I built something tricky here where each part serves as a first blocking part for the other in terms of flipping the value, right? So if you start with 2 zeros, then they both are gonna flip here at the stop edge. Then they're gonna stay like that again and up until go again and go this way. Then they're gonna go down, right? So it's the same. Remember when I explained the flip-flop is the best way to think about it is you have two, you had a water pipe, right? And you have two gates, right? And you can open one and close another one. So when you open the first one, some water goes down, but it doesn't go all the way through the pipe. They just go to half of the channel, right? And then it's blocked by this guy. And then you, at the same time, you move both gates, right? 1 to 1, 1 to 0, and one gate's open. So whatever piece of the water you had goes through, and the rest is blocked. And to get another piece of water next time, you need to go the full-blown cycle, right? And then you can imagine someone just magically every 1 nanosecond doing this trick, moving those gates up and down. That's essentially how the flip-flops work, right? They always let you to just get a little bit through, and the other part blocks this signal through, but it's not completely wasted. It memorizes what you were given it as an input, and then whenever time comes, it passes it through. So the difference with the water analogy, we're not just pass the same water, we might pass the value of 1 or 0. Okay, this is pretty much a few example cases I want to have for you to practice at home, to understand the material of today's lecture better. Based on your feedback, you probably noticed your quiz didn't have a lot of questions on the fresh material, right, today, but it will be there on the next week quiz. So please try to understand, ask questions in Piazza, and work on your labs. And this is pretty much everything I have for today. So if there is anyone who wants to talk, has some very specific questions that were not answered in Piazza in today's lecture and want to talk, please send a message through Zoom, and I would place you into the waiting rooms, and then I meet with all of you one-on-one. But otherwise, yeah, someone is asking when our term tests again. There is no midterm test, so we remove the midterm test, so focus on your labs instead. You're gonna have a take-home final, but there is no midterm, so a little bit less work for you. Okay, so thanks everyone. Have a nice weekend, and if you want to stay and ask questions, please just let me know so I know you are really waiting for feedback, not you're just not waiting in Zoom. Thank you, guys. Hello.
Hello. Can you hear me?
Yeah, I can hear you. It's not very loud, but I can hear you.
Okay.
So you said you had a question about the quiz.
Yes, I did. Just some clarification.
Yes.
Okay, are you able to see my screen?
Yes, I do.
Okay, so I got these two questions wrong, 2 and C.
Yeah, you essentially, I guess you got confused with what signed versus unsigned means. So you were getting the right answer in the opposite direction, right?
Yeah. So I guess I was confused what overflow meant, because in this slide, I guess this addition overflows because it becomes negative. So is that like the only definition of overflow?
Yeah, essentially what happens is that the overflow, the value becomes incorrect because you overwrite the sign bit with the results of addition or subtraction, right? So the overflow means that you add up the value, but whatever you get is actually not correct value because you corrupt the sign bit. And you can corrupt it two ways, right? You can corrupt it by adding two large numbers, right? Right? And well, not two large numbers, but large enough. So after you add, it doesn't fit into, say, 5-bit or 6-bit precision, right? And then it becomes look like negative, which it shouldn't, right? It just doesn't have enough bits to store the positive value. And the same thing can happen for negative. You might get too small of a negative number that doesn't fit into this stuff, so it becomes look like positive, right? So that's what happens.
Yeah, that makes sense. So for this addition,
essentially, it's like, don't take it like the good thing you would learn it right now, right? So the thing is, you actually got the process correct. You just didn't understand when the overflow happens or not. So you did the right process. It's just in one case, that's where the overflow happens because you were not supposed to get, the addition of these two numbers shouldn't lead to 0, 0, 1. It leads to overflow, right? But when you treat them unsigned, then one of them is negative, then that's actually a correct answer. There's no overflow there. Because
so when I add these two numbers, am I correct to get a additional bit that doesn't fit?
Can you repeat your question again?
So when I add A and C together, on my paper, I get a additional bit that doesn't fit in the 8 bits.
So what happens, that bit goes into sign and corrupts the sign bit, right? That's what the overflow means. So essentially, or even if you don't store it, the problem is if you look at the output, right? So you see you're going to get the output that actually not correct, right? It's like if you look at this just means that the result is 1, right? Yeah. And that's because you just don't have enough bits to store the results. So usually what happens in when you're going to learn about assembly language, the operation, it's going to set an overflow bit for you. So the architecture, like x86 Intel processor, is going to send you a bit saying you get an overflow. And then you need to correct it, right? So you know you get it, right? So, but that's also the situation if you're going to write it in C and add this up, right? This is sometimes people get truncated numbers and they don't understand why this happens. It's because of the overflow.
Okay.
Okay.
Oh, wait, were we talking about signed or unsigned?
Here we're talking about signed.
About signed? Yeah.
In the unsigned case, you see that one of these guys would be negative, like it's a 2's complement representation. Okay, I think you got it right now. It's just you're confused between signed and unsigned and what overflow means. I hope you get it right now.
Okay, yeah, okay, thank you.
Sounds good?
Yeah, thank you for your time.
Asking the question. Okay, I'm leaving, guys. So if you don't have any questions, have a nice weekend. Bye.